Assalamualaikum warahmatullahi wabarakatuh. So we are from group 3. We'll be presenting our group project for computer aided design BDX10812. So what is CATIA? CATIA V5 is a powerful 3D design widely used in the aerospace industry to ensure the aircraft components are safe, precise and accurately modeled. This group project provides students with hands-on experience using the software to design individual aircraft parts, focusing on the creating detailed 3D models and accurate 2D technical drawings. So by applying engineering principles to these designs, we can improve our visualization and problem solving skill. Furthermore, this project encourages teamwork and critical thinking, helping us to prepare for complex engineering tasks in the future by bridging the gap between the classroom theory and practical industry application. So for the first component, which is vertical tail stabilizer. Vertical tail stabilizer provides directional or yaw stability by producing a restoring yawing moment when the aircraft experiences a side slip, thereby aligning the aircraft with the relative wind and maintaining straight and stable flight. So it is aerodynamically integrated with the rudder, ailerons and yaw damping system to provide effective yaw control, coordinated flight and suppression of instability such as dash roll. So structurally, the vertical tail stabilizer is designed using lightweight spars, ribs and stress skin to withstand aerodynamic, gust and asymmetric thrust loads while preventing failure, fatigue and aeroelastic instabilities such as flutter. Although it significantly enhances flight safety and engine out controllability, it also introduces additional drag and weight, requiring careful optimization to balance safety, fuel efficiency and maneuverability. So for the first process, which I make the vertical tail stabilizer first, and this is the part design and surface modeling for the first process. So for the next one, I use wireframe to create rudder at the vertical tail stabilizer. And this is the 3D modeling for my part design. Lastly, for my part, discussion and analysis, which contains machining process and material selection for vertical stabilizer with rudder. So usually they use CNC milling and boring as the machining process, and the material selection aluminium alloy, titanium, CFRC, stainless steel and bronze.
Hi, my name is Masha Sudan and my metric number is AD250048. In this project, I choose the horizontal tail stabilizer. So for this component, it ensures an aircraft longitudinal stability and also pitch control. It works by counteracting unwanted movements to keep the plane stable so that it's easier for the pilot to take off and descend smoothly. Okay, so in this modern era, the components are built from lightweight, high strength composite to provide maximum durability and aerodynamic efficiency without adding any unnecessary weight. Next, for the sketch part, I use XY plane, and then I use profile to do the sketch, and instead of using line or rectangle, this is because if I use line or rectangle, it takes so much time to complete the part design. And then I also do the constraint to determine the length, and lastly I use the mirror method to complete the part design. After sketching, I use that to do the modeling. Next, after do the 3D modeling, I will do drafting and also orthographic. In this drafting and orthographic, I use third angle projection, and for the ratio I use 1:4, and for the material is hardened steel. And then I also use dimension to show the length and also the angle. In the drafting also I show 3 view, which is top view, front view, and also side view. It is easier for people to know how it looks like from each view. Next, horizontal stabilizer only suitable for 3 machining process, which is CNC lead milling machine operation. Number 2, CNC EDM die sinking and wire cut operation. And number 3 is CNC grinding operation, machine operation. This is because conventional way is a high risk for workers to use, because we have to face a minor error, which is the component will automatically be reject. So to avoid it, we use CNC for the machining process. And for the material selection is I will choose hardened steel because it is the most suitable for aircraft components.
Assalamualaikum, my name is Nur Aina Najra binti Hassan. My matric number is AD250042. And for this part, I will explain about my component of the project. So I choose turbine engine. Turbine engine aircraft use gas turbine jet engines for propulsion, working on the principle of continuous compression, combustion, and expansion of air to generate thrust, powering various aircraft from airlines to fighters, with common types being turbofan, turboprop, turbojet, and turboshaft, all relying on a core cycle to spin blades, drive compressor, and create powerful, efficient flight. Okay, so for this step, the modeling process starts in the part design workbench. First, a 2D sketch of the shaft profile is created with the required dimensions and constraints. This sketch defines the basic shape and length of the shaft. After that, surface modeling is used to define the geometry. Surface features allow smoother transition and better control over complex contours along the shaft. This combination ensures the shaft has accurate dimension while maintaining a smooth surface finish suitable for further operation. Next, the model is developed using the wireframe and surface design workbench. Reference curve, guidelines, and points are created to control the overall geometry. Using this reference, the revolve function is applied to generate a symmetrical surface around a central axis. This method is especially suitable for circular or cylindrical components. Revolving the profile ensures uniform geometry and improve modeling accuracy while reducing design error. In this final process, the surface modeling sweep function is used to create repeat blade or fin shapes along a defined path. This allows complex shapes to be formed consistently. Then the array function is applied to duplicate these features evenly around the central axis. This significantly reduces modeling time and ensure perfect spacing. Finally, part design is used to combine all features into a complete and fully defined component ready for analysis or manufacturing. So this is the 3D modeling of the overall process. So for this part, I will explain to you machining process and material selection. For aircraft and shaft, machining process is the name milling, grinding, and ADM. For material selection, we use nickel superalloy, Inconel 718, and Inconel 625. For inlet case, machining process is CNC milling, EDM, and drilling. For material selection, we use composite material, carbon fiber reinforced. And for the fan, machining process is CNC milling, 5-axis, grinding, and EDM. And the material selection, we use carbon fiber composite or titanium alloy.
Hi, Assalamualaikum. My name is Nur Erika Nafisha. My metric number is CD250103. We'll be presenting component number 4, that is aircraft main landing gear, which support the aircraft during landing, takeoff, and ground operations while absorbing impact loads. This assembly consists of three parts: axle, wheel hub, and tire. The tire is not included in the machining process because it is not a metal part and it is not part of the project requirement, but it is shown to visualize the complete assembly. The sketch of all of the three parts are drawn to show their shape and key features before creating ISO standard mechanical drawing. The axle is sketched along the side view centered on the center line, as it will be revolved to form a cylindrical shape. The wheel hub is sketched below the axle, showing the profile from the left to right, and also will be revolved into the new existing line that was created. The tire is sketched on top of the wheel and revolved to form a circular shape, showing its position in the assembly. All sketch include proper dimension in millimeters, hidden line, centerline, and alignment of views to ensure clarity and accuracy for manufacturing. This is the 3D modeling of main landing gear that has been created with the help of the sketches. Next, I will explain the machining process and material selection for each part. The axle is machined using milling because it allows accurate dimension and precise functional features. The material is alloy, chosen for its high strength, toughness, and fatigue resistance, which is essential to withstand repeated landing loads. The wheel hub is machined using a combination of lathe turning, milling, and grinding. Lathe turning produces the cylindrical features and central bore, milling creates the mountain slots, and grinding ensure high dimensional accuracy and smooth surface finish. The material is also alloy steel, selected for its strength and durability. Lastly, the tire is included only for assembly visualization, and it is not machined, as it is manufactured using rubber molding process. Its inclusion shows how it fits with the axle and wheel hub in the assembly. In conclusion, this project successfully achieved its objective by providing hands-on experience in designing and modeling aircraft components using CATIA V5. We improved our technical skills by creating precise 3D models and professional 2D drawings that meet established engineering standards. By turning a conceptual design into digital models, we develop better problem solving and critical thinking abilities, especially when addressing design challenges during the modeling process. Furthermore, strong teamwork and collaboration ensured that all components were integrated smoothly and accurately. Ultimately, this project served as a vital link between theoretical engineering knowledge, practical and real-world application.